This section, section 6.2, is introducing the binomial distribution. Now there's a lot of ideas that we need to get used to here, and if you've not looked at this before, or even if you have looked at this before, it might seem at first as though I'm starting off on one tack and then we switch roads and start talking about something else, but by the end of it you'll see how it all fits together. There's all sorts of different ideas that we need to get a full understanding of the binomial distribution and where specifically where this formula comes from. So let's make a start. The first thing we need to be able to do is identify if we have a probability experiment which is a binomial kind of experiment, i.e. A random variable. So a random variable, let's say capital X. We can think of that as the outcomes of the experiment. We can think of a random variable as basically being the same thing as an experiment, can't we? It's all of the outcomes of the experiment and it's one particular value that the experiment has taken as its outcome. And that random variable then can take probabilities as defined by a probability distribution. So if we've got a binomial experiment, then we can say that it's distributed with particular probabilities, which will be these numbers that we would put in these spaces in the bottom row of the table. So the first thing we need to know is that if an experiment is modelled with the binomial distribution, the outcomes of the experiment are the top row of the table, and they are 0, 1, 2, 3, 4, 5, up to n. Those are the outcomes of an experiment if the experiment can be modelled with a binomial distribution. It's called the binomial distribution. That means it's a probability distribution. That means that we know the bottom row of the table. We know the probability of this experiment coming up with an outcome of 0, and an outcome of 1, and an outcome of 2, and an outcome of 3. And the brief version of this is that formula there gives you those probabilities for the bottom row of the table. Okay? So that's the idea. We've got all sorts of different probability experiments. Each experiment can have a random variable attached to it. A random variable is the outcomes of the experiment that go in the top row of the table. We can assign probabilities in the bottom row of the table. And in this particular case, with the binomial distribution, we know what those probabilities are. Okay. If you think about the probability experiments that could exist in the real world, so for example, go and stand by the side of the road, look at the next car that comes along and see what colour that car is. Well, the outcomes for that experiment would be things like red, yellow, green, blue, different colours, and they would go in the top row of the table. The bottom row of the table would be the probability distribution. That would be what's the probability of seeing a red car, probability of seeing a blue car, probability of seeing a green car. Now, there's an example of an experiment where it'd be very difficult to find out the probability distribution. We'd have to take all sorts of surveys about numbers of cars, and even then we'd have to do it through experimental data. We couldn't work out theoretically what the probability of seeing a red, green, blue, yellow, whatever other colour car is. We wouldn't be able to work out these probabilities for the bottom half of the table. The reason we're looking at a binomial distribution is that we have a formula that gives us the bottom row of the table. If we have an experiment that fits the binomial distribution, then we can work out the bottom row of the table. So that's what we're looking at. So the next big question then is, okay, I've talked about this, the fact that the outcomes are 1 to n, and I've talked about it being a binomial experiment, but how do we spot, when we hear a probability experiment described, how do we spot that it is a binomial experiment? This is the list in the book, page 88 at the bottom. There are 4 bullet points there. We'll come back to those in a minute, but first of all, let's think of it like this. The thing I always suggest that people think about is you're flipping a coin 10 times, how many heads do you get? Okay? So you flip a coin 10 times, it doesn't have to be a fair coin. So let's say for the sake of argument, it's a biased coin, the probability of getting heads is 0.2. How many heads do you get on that coin if you flip it 10 times? Well, I could get no heads, 1 heads, 2 heads, 3 heads, 4 heads, up to 10 heads on that coin, okay? If the probability of getting heads is 0.2, then I'd expect the probability of 2 to be the highest number in the bottom row of the table, the probability of getting 3 a little bit smaller and 1 a little bit smaller, but there's still a possibility that I get 10 heads on that coin. I could flip a biased coin 10 times, even if the probability of getting heads is only 0.2, I could get 10 heads in a row in theory, so there is a number that we can find that goes in the bottom row of that table, okay? So a binomial experiment is one which is like that situation. You're flipping a coin and you know the probability of getting heads, doesn't have to be a fair coin, and you flip it 10 times in a row, count how many heads. So let's look at this in general then and see what I mean by an experiment which is like that. First of all, every experiment which can be modelled with the binomial distribution, which I will, from now on, I'll call it a binomial kind of experiment. So a binomial kind of experiment, you've got a little experiment which is called a trial. So in our example here, that little experiment would be flipping the coin once. And the trial can have two outcomes. One of them we'll call success and one of them we'll call failure. So on this example, getting a head we called success, getting a tails we call failure. There's no reason that the word success doesn't have to be particularly relevant. Getting a head doesn't have to be winning. You know, heads and tails, there's no reason that heads is winning and tails is losing, is there? And you'll find later on that it's a bit unfortunate that we've got the words success and failure, because sometimes you've got two outcomes and the one that we label as success feels like it's the opposite of success. So for example, we might be doing a medical trial saying, does this pill cure people's headaches? And we might say that success is somebody's headache not being cured because it will make the maths easier in the rest of the question. So it doesn't matter what we call them, but we've got two outcomes for each trial. Heads or tails, success and failure are the labels that we give them. Okay, we could call them outcome 1 and outcome 2 or something like that, but we call them success and failure. So each trial has a success or a failure, and those are the only outcomes for the trial. You do that trial a fixed number of times. So you decided before you start, we're going to stop after n trials. So in this experiment here, we said n was 10. We said we are going to flip this coin 10 times. We didn't say we'll keep flipping it until we've got 6 heads. We didn't say we're going to stop flipping it after 7 tails. We said we're going to flip the coin 10 times and see what happens. And then we count how many successes we've got. The probability of success is P, and that has to be the same at every trial. So when I flip this coin, I can't use this coin, this bias coin once, and then change to a different coin. The probability of success has to be the same for every single trial. And then the trials have to be independent. So getting a head on or a tail on the first toss doesn't change the probability of getting a head or a tail on the second toss, okay? So that's the situation we're looking for. A lot of people get mixed up between a trial and the full experiment here. So just a quick reminder, a binomial experiment, you perform a trial. A trial has two outcomes, success and failure. You do that a fixed number of times, 10 times, 20 times, 50 times, and you count how many successes did you get. So the final outcome of that whole process has to be a number, doesn't it? If you flip the coin 50 times, how many heads did you get? The answer to that question has to be 0, 1, 2, 3, 4, 5, 6, 7, 8, one of those numbers between 0 and 50. A lot of people get confused with this, and what's a really common experience in my lessons is that we have a lesson introducing the binomial distribution, and in the next lesson I'll come in and I'll say, okay, so what are the outcomes? If I've got a random variable and I tell you that it is distributed with the binomial distribution, what are the outcomes? And people say, oh, success and failure, which is mixing up the trial and the full experiment. So each trial has to have success and failure, but the binomial experiment is we're counting how many successes we've had, okay? Just quickly, we also say if x is a random variable, we say is distributed with the binomial distribution n and p. So we read this, x is distributed binomially with parameters n and p, n being how many times we are carrying out a trial, so how many trials we're doing, and p being the probability of success at each trial. Okay? So at this point, it's perhaps useful to look forward through the examples and see the sort of things which are binomial experiments. I'm saying things that are like flipping a coin 10 times, seeing how many heads we've got. So let's have a look at example 5. We have a class of a reading group, in fact, and we're interested in whether they're left-handed or right-handed. The probability of somebody being left-handed is 0.15, okay? We take a random sample of 20 members of this group. So, do we have these things? Well, there's a fixed number of trials. Yeah, we said we're going to do 20 samples. There are two possible outcomes, success and failure. So in this case, left-handed success, right-handed failure. Okay, again, there's no advantage to being left-handed or right-handed, it doesn't matter, but we have to call one of them success and one of them failure. It doesn't matter which way around we label it. There's a fixed probability of success. It says in the question, the probability of being left-handed is 0.15. We've no reason to suspect that that's going to change throughout the course of the experiment, but we are, I suppose, we're making an assumption that that this sample of 20 doesn't materially change the sample size, doesn't importantly change the sample size. So, for example, if this was a reading group that contained 2,000 people and I take a sample of 20 out of it, then the probability of picking somebody left-handed stays pretty constant. If it's a reading group of sample size 21 and I'm taking a sample of 20, then I've got a problem with the probability of success staying the same, and I've got a problem with the trials being independent, because once I've sampled one person, that affects what happens with the next person. But we're making an assumption here that this is a large group of people, so taking a sample of size 20, the probability of picking somebody left-handed is remaining constant. Okay, or I suppose the other assumption we could be making here is that we pick somebody at random out of these 20 people. Maybe there are 20 people in the group, or 30 people in the group. Maybe it's a small number of people in the group, but I pick somebody and then I put their name back in the hat, in which case the probability of picking a left-handed person is 0.15 and stays constant. So we're having to make some assumptions in order to say that we can use these last 2 points here. But can you see the analogy there of flipping a coin is picking someone and saying, are they left-handed or right-handed? And we're not flipping it 10 times, we're flipping it 20 times. But other than that, it's the same sort of experiment. Let's have a look at another example here. So we've got a sample of 20 bolts from a large batch which are checked for defects. The production process should produce 1% of defective bolts. Okay, so the probability of getting a defective bolt is 1%, and we're picking 20 bolts from a large batch, so we can assume that the probability of getting a mistake is constant, and the probability of getting one bolt defective is independent of the probability of the next bolt being defective. So we can assume that we have these last 2 points here. Then, do we have a fixed number of trials? Yes, we do. We've decided before we start we're going to take 20 bolts, and success and failure at each trial. So in this case, success would be finding a defective bolt. So success is actually, the bolt is failing, isn't it? So it's, but like I say, success and failure, doesn't matter which one we label which. And then let's see, the dice is biased, so the probability of it landing on a 6 is 0.3. Hannah rolls the dice 15 times. So, okay, 15 times, that's 15 trials. A 6 or not, so that's success and failure. Fixed probability of success, because the dice isn't going to change. Independent trials, because one roll of the dice doesn't affect the next roll of the dice. Okay? So, summary so far. If we've got a random variable which can be distributed with a binomial distribution, it has to follow these rules. If we've got an experiment which you see described in a set of writing, or someone tells you about it, if you are listening to that explanation, or you're reading that explanation, you're thinking, oh, right, so there's a fixed number of trials, there's success and failure at each trial, the probability of success is fixed. And if we've got all of these things, then we know that that experiment can be modelled using the binomial distribution, which is as much as to say that the outcomes of the experiment are the whole numbers from 0 up to n. N is how many trials you've done. If we've got all of that, then we know how to work out the bottom row of the table. We know how to work out these probabilities in the bottom row of the table. And the way that we work them out is using this formula here, okay? Now, you might be looking at that formula there and thinking, well, that's all well and good, but I don't know how to use that formula there because it has this funny notation NR that looks like a vector, and that, if you've not met it before, stands for N choose R. This might be where you remember the core chapter on the binomial theorem, and this is maybe where this starts to ring a bell. It looks very like part of the binomial theorem chapter. I'm not going to assume that you've done that chapter on core, so we'll go through where this formula comes from. But the big picture here is a binomial experiment follows these rules. The outcomes are 1 to n, and the probability of each of those outcomes happening can be worked out from this formula. If we know how to use this formula, then we can start answering questions like, if x follows the binomial distribution, we do 12 trials and the probability of success at each trial is 1/6, what's the probability of getting the outcome 2 on the experiment? What's the probability of getting the outcome 9? And we can say, what's the probability of getting less than or equal to 1? Because that's the same as saying, what's the probability of getting a 0 or a 1? So we find the probability of a 0, find the probability of a 1, and we add those two together. Well, the way we find those numbers is using this formula. Now, I'm going to stop this there. That's the first part of this. Next thing we need to know is where does that formula come from and how do we use it? And we'll do that separately in the next video.